In Chapter 7, we're going to be looking at the periodic table and periodic properties of the elements. We're going to start with this picture. This is the periodic table, and it lists each element by year of discovery. And I like looking at this because it gives us an idea of what of what elements were discovered over time. If you look at the ones that are listed in gray here, those were all present in their elemental form before in prehistory. So those were found by people before they even knew what chemistry was. When you get to the yellow ones were discovered between the 17th and 18th century, so 16 and 1700s. Most of those in the 1700s, just a few of them here in the 1600s, just that one actually. And then the sort of light green ones, those are the ones that were discovered in the 19th century. And then the blue ones in the 20th century, and the pink ones down here in the 21st century. You'll notice that the 19th century was very productive as far as discovering elements, and that's when most of the elements were discovered. In the 20th century, most of the ones that were discovered were transuranium elements and some of the unstable elements like technecium and stuff. And in the 21st century, it's just been sort of filling in that last little bit. There hasn't been anything past element 118. So, okay. So we're going to talk about Dmitri Mendeleev, who is widely considered the discoverer of the periodic law and sort of the formulator of the first periodic table. Although I will say that there are a lot more people who were involved in the development of periodic properties. And in your textbook, it does talk a little bit about Lothar Meyer, and you can read about that. But we're going to just focus on Mendeleev and kind of move on. So in 1869, Dmitri Mendeleev published the first official periodic table of the elements. He put the elements in order of increasing atomic mass. You have to remember that they don't have atomic numbers yet because they hadn't discovered the nucleus. They didn't know about protons and neutrons at this point. So all they could do was get the masses relative to hydrogen. He placed elements with similar chemical and physical properties into the same columns or the same groups. And those are the things that we call groups now. He said, both the physical and chemical properties of the elements vary periodically with increasing atomic mass. And that is the periodic law. That is the essence of periodicity. He did place several elements out of atomic mass order, and I'll show that to you on his first periodic table here on the next slide in just a moment. He said that the similarities fit better if he placed them out of order. And he also left some blank spaces for elements. It was more than one element, it was for two elements, but he left some blank spaces for the elements, predicting these elements simply had not been discovered. And he even made some predictions as to the properties of those, and I'll show that to you here in a few minutes as well. So here is Mendeleev's very first periodic table. You'll see it is written in German. Most chemistry things were published in German at that time. And you'll notice that the elements are listed a little bit differently, are what we call groups. Like, for example, here is the alkali metals, lithium, sodium, potassium, rubidium, cesium. They're listed, they're horizontal instead of vertical. In his next periodic table, the one that was a couple of years later, he went the other way with it. But in this first one, he did this. So several key features that I want to point out. Look at the placement of tellurium. So oxygen, sulfur, selenium, tellurium. Well, tellurium, if you look down this list, you'll see that all of these elements are in order of increasing atomic mass. But tellurium is out of order, so he put a question mark there. And he said, tellurium fits better with, oxygen, sulfur, and selenium, and iodine, which is J in this particular version, fits better with the halogens, so fluorine, chlorine, bromine, and so J, iodine, is right there. Well, he said it fits better, and he was right. It does fit better. The thing that I want to point out about that is this kind of interesting is that Mendeleev actually thought that people were just measuring the atomic mass of tellurium wrong. He thought maybe that they were just measuring the tellurium wrong, and he was convinced of that for a long time. It wasn't until people had researched it much longer that he finally was convinced that it was just bigger. There are some blank spots. So notice the blank spots here between zinc and arsenic. And that is where on our modern periodic table we have gallium and germanium. And so he called it eka aluminum for gallium and eka silicon for germanium. You'll also notice that there are no noble gases. The noble gases were not discovered until the 1890s, which is kind of remarkable. So, okay. Well, here is Mendeleev's 1871 periodic table, and you'll notice that it looks a lot more like our modern periodic table, although it's just definitely different, but it looks a lot more like our modern periodic table than the previous one. We have our group numbers. We've got vertical groupings of the families, and he also has oxide formula. So R2O. It's a little bit difficult to read there, but R2O for group 1, which that is definitely how that works. R2 or R3O2 for R2O3 for group 3. That's an example there. He's also got the formulas with hydrogen. So you can see that that things were starting to look a lot like this. Again, here is eka aluminum, what he called eka aluminum, and eka silicon. And he said these things just simply haven't been discovered yet. And he made some predictions as to their properties. And I'm going to show you that on the next page. All right, still no noble gases because, like I said, they weren't discovered until the 1890s. So here is a comparison of what he called eka silicon. He made the prediction in 1871. He said the atomic weight of eka silicon was 72. When it was later discovered, it was found to have an atomic weight 72.6 approximately. My version of the periodic table right now reads 72.63, but that could be just due to variations in the way that atomic masses are defined. Density of 5.5, and the actual density was 5.35. That's very close. Specific heat of 0.305. It was 0.309. Essentially, if you have the mass right, you're going to get that specific heat right. The melting point, he just said high. He wasn't going to predict a number there, but 947 degrees Celsius. That was not too bad there. Color, dark gray versus grayish white. So pretty close. Formula of the oxide, XO2. So it would be 2 oxygens for every one of those elements, every one of those atoms, and that definitely is the case with germanium. The density of the oxide, 4.7. Very good prediction there. Formula of the chloride, XCl4, GeCl4. So you see that matches up. And the boiling point of the chloride, a little under 100, and it was actually 84. So very good predictions of the properties for germanium. Now, I will say he made some predictions that were not very good, but he was able to make these predictions. All right, and then here is Mendeleev's 1898. This was revised after Marie Curie discovered radium. It's RD right here on this periodic table, and the modern one, it's RA. They didn't have standardized symbols until a little bit later. And it also includes the noble gases that were discovered in the 1890s. And so, so here you'll see he has it listed in group 0, and we, of course, have it listed in group 8. All right, and again, this is remarkably similar to the modern periodic table. The only thing that is different is that we don't have the transition metals separated out, and it wasn't until later that they were able to separate out those transition metals. All right, still some major changes to come. So we want to look at Henry Moseley, and Henry Moseley gave us the notion of the charge on the nucleus, how much charge was on the nucleus. Over here, you'll see a picture of Henry Moseley. He was a British citizen, and at the time of his discovery, he was in his young mid-20s. And so what he did is he took elements and bombarded them with high energy electrons. When the high energy electrons ran into the metal, they would eject the electrons, and then the electrons would fall back in, and you would get X-rays. Well, he found that the square root of the frequency of those X-rays was proportional to the charge on the nucleus. And that charge on the nucleus, of course, is the atomic number. And so this was a very important discovery that Moseley made. It was it gave us the atomic number. It made it so that you could definitively tell where there were elements. It made it so that things that people thought were elements, they were able to rule out. And then blank spaces, including some from Mendeleev, they were able to determine that there really were blank spaces. Some of those were discovered decades later, well after Moseley. Some people didn't really believe that he could do this, but he was able to do it. In fact, a chemist named Georges Urbain, and I'm probably saying that wrong, he had isolated some rare earth elements that were very similar in chemical properties, and he had claimed that he had isolated each one. And he came to Oxford and met with Moseley and said, "Here, I'm giving you this mixture of rare earths. Can you tell me which ones are there?" Well, after about an hour, Moseley came back and said he identified each of the elements in there, and sort of his legend was born. Now, sad little fact about Henry Moseley is that Moseley was, you'll see, I mean, he was a young adult at the time of the beginning of what we call World War I. He joined the British military and was sadly, in 1915, was killed in Gallipoli by a sniper rifle. And that actually had major ramifications for both the military and for the scientific world. Moseley almost certainly would have been given a Nobel Prize had he lived, but that unfortunately he did not. So we want to look at our in-class assignment number 8 here. And these are both easy questions. In the period from about 1800 to 1865, the atomic weights of many elements were accurately measured. Why was this important to Mendeleev's formulation of the periodic table? Well, Mendeleev put the elements in order of atomic mass. So Mendeleev put So without those accurate measurements for atomic mass, there's no way that Mendeleev would have been able to do this nearly as accurately. What property of the atom did Moseley associate with the wavelength of X-rays emitted from an element in his experiments? And the property was the charge on the nucleus. And then in what ways did this affect the meaning of the periodic table? Well, it gave us the atomic number. All right. And by giving us the atomic number, it sort of froze in place where individual elements were on the periodic table. All right. There's so much more to tell about the periodic table. I love this topic, but we don't have the time to put all of that into this lecture. So the concept of periodicity is that we have repetitive patterns. So there may be a particular chemical or physical property that is not necessarily repeating, but very similar as you go through the individual elements. All right. So we're going to find that there are multiple properties that are periodic, and that's going to include the size of atoms and ions. It'll include ionization energy, electron affinity, and chemical property trends for the groups. And we will look at those. Coming up here. Before I get into the next section of the text, I do want to briefly show you electron configuration trends that you may or may not have noticed from chapter 6. So group 1A, if we look at the electron configuration for hydrogen, it's just 1s1. And then if we look at the condensed electron configuration for each of the group 1 elements, well, we have lithium, which has the core electrons that helium has plus 2s1, and then sodium 3s1, potassium 4s1, and you'll notice the trend here is that each of those has one electron in the s subshell, and it's the outer s subshell. And we'll find that that is the only electron in the outer shell, and so we say that those elements have one valence electron. So all of the elements in group 1 have one valence electron. Well, it turns out that that one valence electron is what gives those elements their periodic properties, why they have similar chemical and physical properties. If we look at group 2, we'll see a very similar thing. Beryllium has helium plus 2s2, and you'll see that the rest end in s2. And that's going to give us 2 valence electrons. Now, hopefully you're seeing a trend here. Each of the groups, whatever the group number is, that's how many valence electrons we have. Let's look at group 3, because things get a little bit more interesting when we look at group 3. Here's boron, helium 2s2, 2p1. That's 3 valence electrons. Aluminum, very similar, 3 valence electrons, so s2 and the p1. You'll notice for gallium, we'll see that it's 4s2, 3d10, 4p1. And so we don't count the 3d10 as part of the outer shell. Our outer shell, our valence electrons, are level 4. So 4s2, 4p1, that's 3 valence electrons. Same thing for indium, 5s2 and 5p1. We'll ignore the 4p10 because they are not in the outer shell. For thallium, we'll see for thallium that we actually have some F shell electrons that are counted here, but again, those are in level 4, not level 6. So level 6 is 3 valence electrons. So regardless of where it is, these elements have 3 valence electrons in group 3. You'll see a similar thing happen in group 4. We'll have 4 valence electrons, so 2s2, 2p2. Similar with silicon. Germanium, again, we have to deal with some d orbital electrons, but that's no big deal. And then 4 electrons for tin and lead. So 4 valence electrons for all of those elements in group 4. For group 5, there's 5 valence electrons. Spoiler alert, 5 valence electrons. So 2s2, 2p3, 3s2, 3p3, and so on and so forth. All right. And then all the way down to bismuth, we'll see level 6, 6s2, and then 6p3 gives us 5 valence electrons for bismuth. All right, let's go to group 6, With group 6, we're going to have 6 valence electrons. Again, that shouldn't be a big surprise at this point. And so we have 6 valence electrons there. For group 7, we'll have 7 valence electrons. So here is group 7, our halogens. So 2s2, 2p5, 3s2, 3p5. And then as we go further down, we'll see some of those other orbitals that show up. But yes, they all have 7 valence electrons. With astatine, good luck measuring that one, but there should be 7 valence electrons. I say that about astatine. Astatine, it's estimated that there's only about 30 grams of astatine in the Earth's crust at any given time. So it's very hard to get any measurements of that. Helium, 1s2. And you'll see that helium is the only one in group 8 that's different. It only has 2 valence electrons because there's only 2 electrons. But the rest of them have 8 valence electrons. So helium notwithstanding, the rest of them have 8 valence electrons. We're going to find that these numbers of electrons, these electron configurations, are key to understanding the chemical and physical properties for these elements. Okay, so for our next section, we're going to look at the concept of effective nuclear charge. This is the charge that is felt by outer shell electrons in an atom. The effective nuclear charge is calculated in this way. You take, so the effective nuclear charge, Z effective, is equal to the nuclear charge, which is just the atomic number, Z, minus a screening constant. And that screening constant is the number of electrons that are in between the outer shell electron and the nucleus. What is happening is that those electrons effectively screen the nucleus from those outer shell electrons so that it doesn't seem like there is as big a charge as there actually is. That screening constant is approximately equal to the number of core electrons. So I'm going to show you how we do that calculation, but I will warn you that that is not an exact, it's not really the exact value for our effective nuclear charge. It's an approximation, and sometimes that approximation works perfectly, and sometimes it's off pretty significantly, but it's as good as we're going to get with what we do in this class. With that, because electrons act like waves and they have these wave-like properties, we'll find that part of the electron density can be closer, and we can actually get fractional numbers for these effective nuclear charges. But don't worry about that. We're going to stick with these whole numbers. So over here, we've got sodium. Sodium is 1s2, 2s2, 2p6, 3s1. There's only 1 electron in that outer shell. And the effective nuclear charge that is felt by it, we're going to calculate that here on the next page. So here is the electron configuration for sodium. And you'll notice that the core electrons are electrons that are not in the outer shell. And then our valence electrons are the electrons that are in the outer shell. So 1s2, 2s2, 2p6, those are all core electrons. So 2 plus 2 plus 6, that's 10 electrons. And for the valence electrons, 3s1, there is just the 1 valence electron. Well, sodium's nucleus has a charge of plus 11. That's the charge on the nucleus. And the charge experienced by the valence electrons is somewhat less than 11 because those core electrons shield the nucleus from those outer shell electrons. And as a consequence, we'll get the charge on the nucleus minus the screening constant. Our screening constant, we're going to say is 10, even though that's not exactly true. It's pretty close. So 11 minus 10, and we get a positive 1 effective nuclear charge. All right, so this electron that is in the outer shell here for sodium, it doesn't experience that full positive 11 charge because there are 10 electrons that are closer. To this electron, that total of negative 10 charge from the core electrons and positive 11 from the nucleus looks like a positive 1 charge. Now, as far as the trends for this, our simplified calculation, which is the one that we're going to use, the effective nuclear charge is always going to be equal to the group number. However, because electrons are in wave functions, they're not point charges, the effective nuclear charge is a bit different. Over here on this graph, I have what the effective nuclear charge. The black line here, and we've got the effective nuclear charge on the y-axis, the atomic number on the x-axis. The black line here represents what the actual charge is on the nucleus. The red one is, this is the effective nuclear charge felt by inner shell electrons. You'll notice that it's a little bit lower, again, because electrons act like waves. All right. Z effective, the green one here, this is the effective nuclear charge based on our simplified calculation, where the screening constant is equal to the number of core electrons. And like I said, that's the number that we're going to use, although if we use some more advanced calculations, taking into account the electron density, we'll see that the effective nuclear charge is a little bit less than the expected, or than the expected value because of the wave-like properties. So there's a couple of different advanced methods we can use for that. Again, we're going to stick with the with this method. The trend we will find is that effective nuclear charge increases as we go across the period. So period 1 has an effective nuclear charge of +1. Period 2, or not period 2. Group 1 is +1. Group 2 has an effective nuclear charge of +2. Group 3 has an effective nuclear charge of +3. Group 4 has an effective nuclear charge of +4. All right. It should increase as we go across. Now, a much milder trend is it increases slightly as we go down in a group. And so let's see, element 6, carbon, is in group 6, and silicon is in group 6. And you see carbon here, the effective nuclear charge in reality is a little over 5. And here for silicon, which is 14, it's, I'm sorry, I got the wrong number there. It's a little over 3, but then for silicon, it's a little bit over 4. So it does increase as you go down in the period. But that, I don't expect you to know. I do want you to know as you go from left to right across the periodic table, it increases. So now that we've covered that concept of effective nuclear charge, we're going to see that it has an effect on other properties like the size of atoms and ions as well. But we're going to talk about atoms first. So we need to come up, there's a couple of different ways that we can measure how big an atom is. A preferred way is to measure the radius. The problem is that the radius is not a easily defined number. If we look at an atom like this atom here that's bonded to another atom, we'll see, it's like, well, where are we going to define the edge of that atom? Are we going to define it where, 95% of the electron density is, 98, 99? Are we going to define it in some other way? And the answer is we're going to define it in some other way, but there's no definitive edge of an atom. Atoms are not like spheres. They're kind of soft. They are wave functions where the electron density falls off as you get further away from the nucleus. So there's kind of a fuzzy edge to these atoms. So one way of doing it is what's called the non-bonding atomic radius. And if you look at atoms, when they run into each other, how close they can get when they run into each other, the closest they can get, that is going to be the van der Waals distance. Half of that distance is equal to the van der Waals radius, or what is called the non-bonding atomic radius. And you'll see that that is indicated here. That number is almost always bigger than what we refer to as the bonding atomic radius. And the bonding atomic radius is the distance between the two nuclei when it's in a bond divided by 2. We also have what is referred to as the metallic radius. And the metallic radius, when you have metals in a crystal, if you take the distance between the nuclei and divide by 2, you'll get the metallic radius. So there's more than one way to measure these radii, and that means that you have to be careful when you're comparing these numbers. So we're going to look at number 17. This is a very easy problem and a very easy calculation. So number 17, the distance between tungsten atoms in tungsten metal, so this is a metal, is 2.74 angstroms. Now, I don't know if we covered this before. If we didn't, then we will now. 1 angstrom is equal to 10 to the negative 10 meters. And that's also equal to 10 to the negative 8 centimeters if you ever need centimeters there. So that is what an angstrom is. I mention that because angstrom, while it is a metric term, it is not an SI unit, but it is related to our SI unit meters. All right, so our radius is going to be the distance divided by 2, or 1/2 of that distance. And our distance here is 2.74 angstroms, and we divide that by 2. Now, we hardly need a calculator to do this, but I'll go ahead and punch it into the calculator just for convenience. So 2.74 divided by 2, and that gives us 1.37 angstroms. So 1.37 angstroms. Looks like I have it still in scientific notation there, but that's not a big deal. All right. And again, that is called the metallic radius, very similar to the bonding atomic radius. So we want to go back here and look at trends. So periodic trends in bonding atomic radii. All right, so these are the bonding atomic radii, and I can tell that there's at least one number, a couple of numbers on here that are not actually bonding atomic radii, because there's a couple of these elements that don't make bonds. For example, neon doesn't make bonds, and if it doesn't make bonds, then we can't get a bonding atomic radius. So they probably slipped in a non-bonding radius there for neon, but we'll forgive them for that. So we'll find that the bonding radius, the bonding atomic radius, tends to decrease as we go from left to right across the periodic table. So you'll see that here lithium 1.28, beryllium 0.96. These are in angstroms, by the way. 0.84, 0.76, 0.71. You'll see as we go across that that bonding radius decreases, and it's true on every one of these. Now, it's not strictly decreasing, because there's some weird stuff that happens in the periodic table having to do with electron shells and stuff like that. But you'll see a definite trend as we go across the periodic table. And the reason for this is because of the increased effective nuclear charge. So lithium, the effective nuclear charge is about +1. Fluorine, it's about +7. As we go through increasing that effective nuclear charge, it holds those electrons more tightly. We'll also find that as we go from top to bottom down a group, that will increase the atomic radius, the bonding atomic radius, because we're increasing the number of shells. So each time we increase, as we go down, we're going to increase the number of shells, and therefore we increase that radius. So let's look at number 23. And on number 23, it's helpful to have our periodic table. So we know that, that the bonding atomic radius increases as we go down, and it increases as we go to the left. So our bonding atomic radius should be really big for elements that are down here in the left corner. And I'll just indicate that. You'll see there rubidium has a really big bonding atomic radius. So increases as we go to the left and as we go down. That's one way to think about it. So now, using only the periodic table, arrange each set of atoms in order of increasing radius. Well, here we've got calcium, magnesium, beryllium. All right, well, there's calcium, magnesium, beryllium. Beryllium should be the smallest because it's the furthest up, and it should increase as we go down. So it should be beryllium, magnesium, calcium. So beryllium will be the smallest, magnesium will be bigger, and calcium will be bigger than that. Next, we have gallium, bromine, and germanium. All right, so here's gallium, germanium, and bromine. All right, it decreases as we go to the right, which means it increases as we go to the left. So bromine should have the smallest bonding radius, germanium should be bigger, and gallium should be bigger than that. So we'll do bromine is smaller than germanium, which is smaller than gallium. Finally, here we've got aluminum, thallium, and silicon. Aluminum, thallium, and silicon. All right, so let's find those. Here's aluminum, silicon, and there is thallium. Let's do aluminum and silicon first. It should be bigger as we go to the left, so silicon should be smaller than aluminum. We'll go ahead and write that down. So silicon is smaller than the aluminum. And then here we have aluminum and thallium, and so since thallium is further down, thallium should be bigger, so we'll say aluminum is smaller than thallium. And by the way, if you ever get a chance to work with thallium, I'm going to say don't. It is extremely poisonous, and it's a good way to poison yourself by working with thallium. So unless you really know what you're doing, don't work with thallium. All right, so now we want to look at ionic size. So this is the size of the ions. So we're going to find that cations are smaller than their parent atoms. And as evidence of this, let's look at, so here's lithium, and there's lithium ion. You'll see the lithium ion is smaller than the lithium. And this is true for every single one of these orange ones. These orange ones are all cations, and they are all smaller than their corresponding parent atom. What happens is that when you remove an electron, from an atom, you decrease the number of repulsions between the electrons, because you're removing one of the electrons, you're going to have fewer repulsions. By doing that, that means the remaining electrons are going to be pulled closer to the nucleus. So removing decreases the number of repulsions, which causes the remaining electrons to move closer to the nucleus and make the cations smaller. Anions, on the other hand, that's when you've added electrons. They're going to be larger than their parent atoms. And so the reason for this is that when you add an electron, it increases the number of repulsions, which causes the electrons to spread out. You still have the same charge on the nucleus, it's just that there are now more electrons. So here's oxygen, and the oxide, you'll see, has a larger radius. Same thing there for fluoride. All of these ones here that are in blue, they are bigger than their corresponding atom. So let's look at number 25 on our in-class assignment. All right, and here we're going to use the direct quote that I had there on the screen. Why are monatomic cations smaller than their corresponding neutral atoms? And the answer is removing an electron decreases the number of repulsions, which causes the remaining electrons to move closer to the nucleus. All right. And again, you will find that this is just that right there. So removing an electron decreases the number of repulsions, which causes the remaining electrons to move closer to the nucleus. On part B, you'll see why are monatomic anions larger than the corresponding neutral atoms. Well, we're going to come back over here. It says adding an electron increases the number of repulsions, which causes the electrons to spread out. Okay, I paused the recording for a second so I could just write that down so you didn't have to watch me record that. Or yeah, you didn't have to watch me write that down. All right, so why does the size of ions increase as one proceeds down a column in the periodic table? So, in other words, why is it that our cations over here, so why lithium, then sodium's bigger, potassium's bigger, rubidium's bigger? Likewise, the anions are the same. Fluoride, and then chloride's bigger, bromide's bigger, iodide's even bigger. So as we go down that column, we will find that those atoms get bigger. All right, so why is that true? Is because we're increasing the number of shells. So we're increasing the number of shells. All right, again, I paused the recording and then just wrote that down. So as you go down in a column, you increase the number of shells of electrons. Okay. So now we want to look at the concept of an isoelectronic series. An isoelectronic series. Well, the word iso, or the prefix iso, means the same. And so an isoelectronic series is a group of atoms and ions all containing the same number of electrons. And in other words, we're going to find that they will have the same electron configuration. We'll find that ionic size decreases with increasing nuclear charge. So the ionic size will decrease with the increasing nuclear charge. So if we look at this series of ions that all have 10 electrons, we will see that as we increase the nuclear charge, oxygen has 8 protons, and if there's 10 electrons, those electrons are going to be fairly spread out. With 9 protons, those electrons will be pulled a little bit more tightly. With 11, now you'll notice neons here because it's measured in a different way, but with 11 on sodium, we'll find the same 10 electrons are held even more tightly, and then magnesium 2+ and aluminum 3+, those electrons get pulled more and more tightly. So as we increase the size, or increase the charge, the size will decrease. So the first part of this is of this question, number 29, what is an isoelectronic series? Well, this is our definition for an isoelectronic series. All right, and so I wrote that down so that that is there. All right, so here it says, which neutral atom is isoelectronic with the following ions? So to determine this, we need to look at our periodic table and see which neutral atom has the same number of electrons as this. So nitrogen has 7 electrons normally, but nitrogen 3-, which is nitride, has 7 + 3. So 7 + 3 will give us 10. That means that nitride is isoelectronic with neon. All right, barium, we come over here, barium is element 56. Barium 2+ is missing 2 electrons, so we'll do 56 minus those 2 electrons, that's 54 electrons, and 54 electrons, that's going to be isoelectronic with xenon. All right, here we've got selenide, so Se is element 34, that has 34 valence electrons. And then Se2- has 2 additional electrons. That's going to make it 36. That will be isoelectronic with krypton. You will see a lot of elements end up, when they become monatomic ions, end up becoming isoelectronic with noble gases. However, that's not the case on this next one. Bismuth, you'll see here, bismuth is element 83. It has a 3+ charge. That means it's missing 3 electrons. So we'll subtract 3 from 83. That gives us 80. It will be isoelectronic with mercury. All right. So let's go back and let's look at the next thing. All right. For ions that have different oxidation states, so elements that have different oxidation states, we'll find that every time we remove an electron, the remaining electrons will get closer to the nucleus. So iron, if we remove 2 electrons, of course, it gets smaller because there's fewer repulsions. Well, if we remove another electron, it gets even smaller. So iron 3 is definitely going to have a smaller radius than iron 2. And again, by removing that extra electron, we've decreased the number of repulsions, and it's pulled the remaining electrons closer to the nucleus. Same thing here with cobalt, copper, chromium. That is the case. So for elements with multiple oxidation states, we'll find that the radius decreases with increasing positive charge. So let's look at number 33, and this will be the last one for this particular video. All right, for each of the following sets of atoms and ions, arrange the members in order of increasing size. So let's just compare selenium, selenide, and selenium. Well, selenium is going to be smaller than selenide because the selenide has 2 extra electrons. So we'll say selenium is smaller than selenide. Now we need to see where telluride fits in there. So selenide and telluride. So since telluride is further down in the periodic table, it has more shells, we would expect it to be bigger than the selenide. So Te2 minus telluride is going to be larger than the selenide. All right, this is one that we just saw on the page there. The Fe3 plus should be smaller than the Fe2 plus, which should be smaller than the Fe neutral atom. All right, and then here we've got calcium 2 plus and then calcium. So we'll do that one. The calcium 2 plus should be, that is calcium there, should be smaller than the calcium. All right, and now we need to look at titanium 4 and scandium 3. Well, calcium 2 plus, there's calcium with 20 electrons. Calcium 2 plus has 18 electrons. It's isoelectronic with argon. Scandium 3 plus, or titanium 4 plus rather, titanium is element 22, but when you remove 4 electrons, it will be isoelectronic with argon as well. And scandium 3 plus, when you remove those three electrons from that, it'll also be isoelectronic with argon. That means that calcium 2 plus, titanium 4 plus, and scandium 3 plus are isoelectronic. And we'll find that for an isoelectronic series, the size gets smaller as you increase the charge on the nucleus. Calcium has an atomic number of 20, scandium is 21, and titanium is 22. So we'll find that the scandium 3 is smaller than the calcium 2 plus, and that the titanium 4 plus is smaller than the scandium 3 plus. All right, well, that's the end of this video. Our next video is going to be looking at ionization energies.